Good morning. Welcome to Krishna's classroom. We continue with our discussions on uniform integrability, which eventually lead to the Vitali convergence here. Now, before that, we have to do some preliminaries, and I was trying to sort of motivate how those ideas came about or how those questions arose. And incidentally, let me just digress a bit and then tell you that I am following the book by H.L. Royden and M. Fitzpatrick on real analysis. This is the 4th edition, which has appeared in PSM. And that is very specific. And I like this book for several reasons, because the earlier version of this I have used while giving lectures on this topic, but the revised version is much more well organized and nicely done. So I thought that maybe it would be nice if I could follow through that, and it is very rigorous. That's the important. It doesn't digress into or go away from the main focus of working on Lebesgue integration theory. I like this book very much, and may also like it. I don't know. Depends on the individual taste also to some extent. Yeah. So we'll go back to the preliminaries for introducing uniform integrability. And last time, I gave some idea of how these ideas evolve and so on, or how the questions come up, because there you need a comparison between Riemann integration and Lebesgue integration. And Lebesgue integration is certainly going much farther from Riemann integration. And Riemann integration is a very restrictive kind of integration. So that we have seen already. So there are some obvious results which are related to this, because you know that in Riemann integration we work with bounded functions on bounded intervals. Okay. Whereas in the Lebesgue theory, we go farther from there and then go to the level of talking about more general functions, maybe extended real value functions, defined possibly on measurable set, what are called measurable sets. And measure itself is a generalization of the length concept for integrals in the context of length concept in the context of Riemann integral is the length of intervals that we make use of. Whereas here we talk about more general class of sets, what are called measurable sets. And the measure is a generalization of the idea of length. Okay, now these kind of generalizations have taken place. So we shall see the results that we are going to work on. Where do they fall? And we have seen that if you take a bounded interval, so in the context of Riemann integration, you take a bounded interval AB are, we can partition this into union of disjoint intervals of length as small as we put it. So given delta positive, there exists a collection of disjoint intervals IN finitely, obviously. That is, AB is IN and such that the length of IN is less than delta. So for any given delta, you can find a partition of the interval into union of disjoint collection of intervals. Now this is an obvious result. It's very easy to devise that. It's no problem. What is important is that you can do it finitely many. What is the analogous result that you have for in the context of what is called Lebesgue measure? Okay. In the context of Lebesgue measure, intervals corresponding to intervals, you have what are called measurable set. And length corresponding to length, you have what you call the Lebesgue measure. And bounded interval, we work with a, so bounded interval that means you have the length of this is less than infinity. It's finite. And correspondingly, what do? We work on, it's not, we don't use this bounded interval. Instead, we will use the following. So, we consider what are called measurable sets with finite measure. That means E is a measurable set with measure of E. Compare the two. I mean, then, okay. Then what do you expect? What do you expect of this result? So if you work with a measurable set, so this result would have the corresponding result here. Let E be finite measure. Now, just remember that this set need not be bounded. For instance, if you take all the rationals, it's unbounded, but it has finite measure. So that's an example for that. So we have measure of E finite. Then what you do is the same sort of statement, given delta positive, there exists a collection of disjoint finitely many disjoint measurable sets AI such that E is now the union of and of course you have this disjoint measurable set. So we have AI intersection AJ is empty whenever I different from J. This condition we have. E is given by this, and such that measure of so for a given delta positive, you can get a collection of subsets of this kind. Now this is the generalization that you have, and I hope everything is clear now. This is the one that we proved last time. Okay, now we go further. Okay. Now we work on what are called integrable functions. Okay. Now just as a sort of preliminary analysis of this, we'll go back to Riemann integral. Okay, so let the class of all Riemann integral functions on AB, and we are working on what are called bounded functions. Therefore, you have infinity. That is there. Therefore, you see that integral A to B we are assuming B greater than, it's bounded. Therefore, F is integrable. Okay. Then what you can prove is the following. Okay. Then there exists a given epsilon positive, there exists a delta positive, and intervals in such that disjoint and such that AB is I'll specific intervals finitely many I'll put it this way. Disjoint intervals finitely many such that again and comma the length of in less than delta and integral over in see what it says is this, that if you take a function on the interval, drawing the graph, so this is the interval AB, then you can partition this into disjoint class of intervals so that given epsilon there is some delta such that the area of f integrated over in is less than epsilon, whereas the length of this interval is less than delta. Okay. So given epsilon positive, there exists a delta. You can adjust the delta such that the area of this strip is less than epsilon, and the length of the interval in is less than delta. So you can partition this interval AB into such sub-collections. That's what we have. Now, what is going to be the analogous result for what you call measurable functions, integrable functions over in the sense of Lebesgue? This is the question that we are asking. Let us try to write down the result and then we will state the theorem. So you see here you are taking a Riemann integrable function. So here what we are doing is f is a measurable function. E is of course a measurable set. Now if f is integrable, here it is, the estimate gives you that it is an integrable function over E. And this is a condition that is integral over E see, this is the Lebesgue integral that we are talking about. Here we are working on what is called the Riemann integral. Okay. So here we are working on the Lebesgue finite then for epsilon positive, that means for any epsilon positive, there exists a delta positive for which if A is contained in E and such that of course I am assuming A is measurable. Measure of A is less than delta, then integral of over A of mod f is less than. Compare these two results. Okay, this part is now taken care of, this by this, and of course I am not using this. I mean, this is not necessary here. Here what I am saying is that for any A which is measurable and such that measure of A is less than delta, this integral is less than epsilon. Okay, so that's the generalization that you have. So we are going to prove this theorem, and then of course you have a version which is converse also. Conversely, if measure of E is finite, now this assumption we have not made there, whereas this corresponds to this. I mean, you know, this interval AB is such that its length is finite. Okay. Conversely, if this is finite, that means we are putting one more restriction, and if for each epsilon positive, there exists a delta positive for which for which for every a measurable subset of E A measurable and measure of A less than delta with less than epsilon and F is E. Here, of course, you need the further assumption that measure of E is finite. And you see that this is, of course, the situation that arises in the case of Riemann integral. Because B minus A is finite. We are working on boundary. So, what it says is that if for each epsilon positive, there corresponds a delta for which for every A contained in a subset of E, A is measurable and measure of A is less than delta with integral over A mod F is less than epsilon, then F is integral. So, this is a sort of converse setting. Okay. So, let us work on this. Now, we shall state the theorem properly. Measurable only let F be integrable on then given epsilon there exists a delta positive for which A contained in E, A measurable is such that measure of A is less than delta, then integral over A of mod F is less than. This is the result that I was telling. That's the statement. Okay. We also make the converse statement. although we have stated it, but then let us properly then prove each one. So I hope you have got an idea of how we speculate certain results from our earlier experience. Here what you have is, we have some experience of working on Riemann integrable functions. Okay. So when you generalized it, you ask what is the analogous result that you can expect. Okay. So we'll work on this. Conversely, if measure of E is finite, now this is an assumption that make, okay, it is analogous to measure of okay, it is analogous to the assumption that that the interval has its length finite. That's already there in the case of Riemann integral. And if for each epsilon positive there exists delta positive, for which for every A measurable, measure of A is less than delta implies with then F is like that is integral over mod F. Okay, so we prove this result. Now, we are not assuming the measurable function is non-negative. May take positive values or negative values, or even extended real valued function is possible. So we prove this by doing it by establishing separately for F plus and F minus. Now you recall the definition of this, and what you have is that F is essentially equal to F plus minus F minus. Both F plus and F minus are non-negative. Okay, that's what you get. And mod F is of course this we have. So we prove it separately for F plus and F minus. Then these relations, with these relations you can combine them. Okay. So at this stage without loss of generality. So all that we need is to prove this for non-negative functions which are integrable. Okay, so it is sufficient to prove this for what are called non-negative measurables, rather integrable. So assume and we don't need this modulus here because we are taking non-negative functions. Let epsilon positive given. Now, by the definition of, see, we have to approximate these functions by a measurable bounded function as closely as we can. By the definition of the integral, there exists a measurable bounded function of course non-negative f epsilon such that 0 less than or equal to f epsilon less than or equal to f on E. And integral over E and 0 less than or equal to integral over E f minus integral over E f epsilon is less than. So you choose such a approximating function f epsilon. F epsilon is different from this in the sense that there are more conditions on this because we are taking it as a measurable bounded function, and this boundedness we can make use of and this. Okay. So what we have is integrability of f assures that the existence of such functions f epsilon. Okay. Now what do we do? Now since on E is a non-negative function which is measurable, that's clear. Then by linearity and additivity over the domains, we have integral over A f minus integral over A f epsilon is equal to integral over A f epsilon and this is less than or equal to integral over E epsilon, and that is equal to integral over E f minus integral over E f epsilon, which is less than epsilon by this choice. Okay. Now you see f epsilon is bounded. It's a bounded measurable function, non-negative function. Now therefore let m positive be such that zero less than or equal to, because it's a non-negative function, less than because it's a bounded function. Therefore integral over A f is less than integral over A f epsilon plus epsilon by 2. That's clear. That is coming from here. Okay. Integral over A f is less than integral over A f epsilon plus epsilon. And this is less than or equal to, now you see that f epsilon is bounded by m, therefore m into measure of A plus epsilon. Now what do you do? We make the choice of okay, we try to make this. So see, we are going to choose A. So we have to choose A such that measure of A can be set at our hand. So we shall do that. Now we shall choose delta equal to so for the given epsilon you have chosen the delta, then integral over AF is less than m into So that's the result. So our statement was that there is given epsilon, there's a corresponding delta, and for a set A, measurable subset of measure less than delta, you have integral over A f less than 0. That's what we have. So that completes the proof. Now we work on the converse. In the converse, we have made an assumption that integral over E finite So this is the assumption that we have made. We shall work on this. What we want to prove, eventually what we want to prove is that this is what we want to prove. This is finite, where measure of E is less than infinity. So that's what we want. What are the given facts? And how do we use them? Now what we assume is that for each A measurable, you have suppose this is what we want to prove. This is the assumption that we make, and this is what we want. Let us suppose measure of is finite. Now you will see that this is crucial in our, and for each epsilon there exists a delta positive for which if A is a measurable subset of E with measure of A less than delta, then integral over A. Now this is the assumption. Now let us use this to come to this conclusion. Okay. Then we claim this is what we want. So what we do is choose epsilon to be equal to 1. Then corresponding to that there is a delta. Okay. So let delta naught be the value of delta corresponding to the choice of So we have chosen epsilon equal to 1, and there is a corresponding delta naught, for which is the delta that you have. Now what we have then, since measure of E finite, we can use the previous theorem. Finite by the preceding lemma, which we have proved already. We may express E as the disjoint union of a finite collection of measurable sets say I equal to 1 to n, it's finite collection, each of which has that is measure of course it's a disjoint union of, so you have EI intersection EJ, I different from J is empty. Then what do you have? Suppose you take any integrable function or any positive function, so this is what you have, k equal to 1 to n integral over k of less than n, because each one of this is less than 1 and therefore this is less than n. We have measure of EI less than delta for I equal to 1 to n. Now by additivity over domains, that means we are taking V to be and with the EI our domains of integration. what we have is the following. If H is a non-negative measurable function of finite support, and H on E, then we have less than n, and therefore you see that the integral is is approximated by this, and f is integrable because this is so. And therefore now this is something that you follow from, okay, because you see that we are approximating the integrable function, we are approximating the function f pointwise almost everywhere through these functions h, for which this is bounded, and therefore you see that their limit is also going to be bounded by, so this is what. So that completes the proof. Okay, right? Now I think the stage is set for introducing the concept of what is called uniform integrability. Now let me just do it in my next class, otherwise we will break the continuity, and look at the uniform integrability and the consequences of that. So thank you very much. We'll meet again in our next class.